To start with, the definition is z-score, and you've already seen this multiple times. But to get a z-score, you subtract away the mean, and you divide by the standard deviation. So a z-score is a way to, it's a way to say, for any particular measurement, how many standard deviations are we away from the mean? The normal distribution shows up really commonly in nature and in engineering and in everyday life. There's a lot of reasons for this. When we say that a random variable is normally distributed, we mean that the probabilities of observing a particular outcome from the normal distribution follow this function. And it's really crazy. It looks complicated. We are not going to directly evaluate the cumulative distribution function, or the CDF. In this class, we are going to use tables. And we've seen this before. To use the standard normal distribution CDF table, you are going to first calculate the z-score of your measurement, and then let's say my z-score is negative 2.37. So I find the negative 2.3. I find the column where I get an extra negative 0.07, and then the value that I'm looking for is at the intersection of this row and this column. So it'd be 0.0089. And on top of this page, there's a little picture which says, you know what, if this is the mean, that's a z-score of like 0, right? Right at the mean, because I'm subtracting mean minus mean, so I get 0. Maybe this is the z-score with negative 2.37, and this table is telling us about the area under that curve. So this sort of bell-shaped curve is describing the probability of the normal distribution, and if you use the CDF table, what you're calculating is the area underneath this curve, because this area underneath the curve is going to be the probability of getting a random outcome less than or equal to that point. Negative 2.37, I guess. It's not the probability of getting exactly that outcome. The CDF is always telling us about the probability of getting less than or equal to that particular outcome. And this is even more important for continuous random variables because, for example, blood pressure, you know, like whenever you do the little cuff and the nurse tells you it's like 120 over 80 or whatever, blood pressure is a continuous random variable. Because if you were to take my blood pressure, what's the probability that my blood pressure is exactly 67.5524? The probability is 0. It's possible that that's my blood pressure, but it's completely improbable that I will ever have an exact predicted outcome for my blood pressure. It's on like a spectrum of real numbers, and I could always have a blood pressure that's close to that, but maybe not exactly there. And so when we talk about continuous random variables, we're never going to talk about the probability of getting an exact outcome. We always talk about the probabilities of getting some kind of range of outcomes. And so the CDF is going to tell us about the range less than or equal to a particular threshold. So we've got the CDF paper in front of you. Also on the back side of that, I've got the quantile function. The quantile function is what you get if you reverse the idea of a cumulative distribution function. Sometimes the quantile function is called the inverse CDF for that exact reason, Because with a CDF, what you're doing is you're calculating a z-score and you're looking up the probability of getting less than or equal to that z-score. But with a quantile function, you are going to input the probability, and on the table you will be looking up the corresponding z-score that represents that threshold. You know, the probability being less than that z-score equals the probability that you want to use as an input that you're looking up. So we'll do some problems with that too. In Excel, there's formulas you can type in to use the CDF and use the quantile function if you are interested. That's of course not going to be on a test because I'm not going to use Excel on a test. Whenever I tell you that a random variable is normally distributed, I'm going to give you the mean and the standard deviation in these types of problems. What you should know is that for a normal distribution, the mean, median, and mode are going to be exactly the same number because the normal distribution is symmetric. And if you have a symmetric probability distribution, like the bell curve we saw earlier was symmetric, then those three measures of central tendency will be the same. You only get different numbers if you have an asymmetric distribution. And then likewise, I'll tell you the standard deviation, so if you ever need to calculate the variance, you just square the standard deviation. Questions about the normal distribution? We'll do examples here in a minute, but any questions for right now?
Will you tell us the standard deviation for all the other ones too?
No. No, I'll tell you how to handle that if it's a different distribution. So changing gears now, we're thinking about a different distribution. Imagine you're out on the lake and you just caught a fish. Now you want to create a probability model for the amount of time that will pass before you catch another fish. How long will it take until I catch my next fish? Suppose you typically catch about 5 fish per day. If we define a random variable to be the amount of time that passes between random events, a random event could be like catching a fish. And we have some expected frequency. And we're going to use the lowercase Greek letter lambda to represent expected frequency. And if I say 5 fish per day, maybe lambda is like 5 fish per 1 day. Or, you know, if I gave you a little bit more information and we say we're going to fish for 8 hours a day, this could be 5 fish per 8 hours. Or something like that. That's what I mean by expected frequency. Then we would say that this random variable follows an exponential distribution. So think for a minute about what we talked about a week and a half ago. We talked about the Poisson distribution a week and a half ago, and the Poisson distribution was saying if I'm given some kind of expected frequency, then the Poisson distribution would tell us the probability of catching a certain number of fish. So the Poisson distribution was a discrete probability distribution because you can only catch 1 fish or 2 fish or 3 fish or 4 fish, right? That's what makes the Poisson distribution discrete. The exponential distribution is now telling us the probability for the amount of time in between these random events of a Poisson-like process. And so once again, we're still going to be given expected frequency. That's kind of similar to the Poisson distribution, except the random variable we care about is no longer the number of fish caught, but it's how much time will pass until we catch the next fish. And the amount of time that passes is not discrete. The amount of time that passes is not going to be just 1 hour or 2 hours or 3 hours, but the amount of time that passes could be like 1.315 hours. You know, the next event could happen at any point in this continuum. So that way, the exponential distribution is a continuous probability distribution. The CDF is not a table. So you don't have to look up a value in a table if we've got an exponential distribution. Instead, what you have to do is you have to write down this formula on your 8.5 by 11 piece of handwritten notes paper you bring in for the test. The CDF is 1 minus e raised to the power negative lambda k. On our nice TI-30X2S calculator, if you want e to the x, you type in the second button and then the LN button to get e to the x. So we'll do some of those examples here in a minute. The quantile function, remember, is the inverse of the CDF function. And so we're going to input some probability that we want, and we're going to get out the measurement. This, in your calculator, you have to use the LN button. So this is going to be like minus, and then your calculator does have a button that says LN for natural log, 1 minus p, and then divided by lambda. So the quantile function in this case would be, if I want to know how much time should I wait until I can be 95% certain I'll catch a fish? That would be a case where I want to input the probability, 95% or 0.95, and as an output, I will get how much time I would have to wait to be 95% certain, or to have a 95% probability. So those types of questions. Again, you can do this in Excel, but you won't be using Excel for the test, so I'll skip over that, and you can look up these notes again later if you want to use it for an Excel. Central tendency is a little bit different for exponential because we are going to be given a parameter lambda where lambda is the expected frequency like the number of fish I plan on catching per hour. And if I want the mean, the distribution mean, that's going to be 1 divided by the expected frequency. If I want the distribution median, that's the natural log of 2 divided by the expected frequency. And the mode of an exponential distribution is always 0. The best way to understand that, I think, is to get on Desmos.com and plot what an exponential distribution actually looks like. And it's going to look like something, I'm going to just use capital L for lambda in Desmos. It's only valid for positive values of x, because that, if you're talking about the time until the next fish, you're not going to have less than 0 minutes until your next fish. And so this distribution only applies for positive values of x, my random variable. And notice that whatever I choose for my, whatever I choose for this expected frequency parameter, the maximum probability always happens at x equals 0. If my expected frequency is low, then the probability starts to shift out to the right. The area under this curve starts to shift out to the right because we expect it's going to take longer until the next catch if my frequency is lower. But if I have a relatively high frequency, then some of that probability or some of that area under the curve is going to shift towards 0, which is saying there's going to be less time that I have to wait until I catch the next fish. But my point is that the mode, the maximum probability, is always 0, which is kind of a bizarre thing, but that's how the math works out. Then the measures for dispersion, that is the variance in the standard deviation, Well, the exponential distribution has an interesting property where the mean of the distribution and the standard deviation of the distribution are actually the same number. It's 1 divided by the expected frequency. And like always, if you have the standard deviation and you want to know the variance, you just take the standard deviation squared to get the variance. So those are things that I would write down on your 8.5 by 11 notes for the test. So I could ask you those questions.
You just always put it under 1?
For the exponential distribution, in general, the variance is just the standard the variance is just the standard deviation squared, right? That's always true for every distribution. The variance is always just the standard deviation squared. The standard deviation is always just the square root of the variance. That's always true. But these formulas that I typed out here, those formulas are only true for the exponential distribution.
Yeah. So do you square root the fraction, or do you square root the lambda and put it over under 1?
Doesn't matter. You could do it in either order. You should get the same answer. Good questions. And then one more we're going to talk about today. This is the last type of distribution we're going to learn for right now. What we're about to talk about, is the continuous uniform distribution. It's not the same thing as the discrete uniform distribution that we learned about a week and a half ago. If I were to open up Microsoft Excel and type in this command, 3 plus RAND parentheses times 17 minus 3, I'll show you what that would look like. RAND, nope, I think it was equals 3 plus RAND times open parentheses 17 minus 3. What it's going to do when I type in this command is every time I hit the F9 button, it's going to give me a new random number between 3 and 17. But what's different about this, instead of just using something like sorry, give me 1 minute. What's different about the command on the top, the one that we're talking about that's new, is that it's not just going to make a random whole number between the lower bound and the upper bound. This is going to create a random real number somewhere between the lower bound and the upper bound. And it can be any decimal, any fraction in between the lower and upper bound. Do you see the difference here? So this is representative of a discrete uniform distribution, where all of the outcomes between 3 and 17 have equal probability. And this is representative of a continuous uniform distribution, because the probability density is still spread evenly between the number 3 and 17, but the outcomes don't have to be whole numbers in that case. Do you feel happy about, do you know the difference between the two? Yeah.
So on the test, how would we know which one to do?
I'll tell you. Yep, I'll tell you. On the test, your questions are going to look like the homework questions. So if you read the homework questions between 2.5 and 2.6, you'll see the slight differences in how I ask the questions. So in this case, if I've got this continuous, uniform, distributed random variable, then the cumulative distribution function, the CDF, is once again telling us what's the probability that my outcome is going to be less than or equal to some threshold k. And that's not a lookup table. You don't have to pull out a sheet and look it up. You just have to use this formula. So put this formula on your handwritten notes. It's going to be the threshold, k, minus the lower bound divided by the upper bound minus the lower bound. That's the probability of getting some outcome in that range. The quantile function, right, is the inverse of the CDF, and there is a formula again for the quantile function where you input the probability you want and then you get out the measurement corresponding to a particular threshold where that probability that you inputted is the probability of getting less than or equal to this threshold that you get as the output from the quantile function. So again, not a table. That's just something you can type into your calculator. So I would make sure you've got this written down somewhere for the CDF of the continuous uniform distribution. You've got this written down here as the quantile function of the continuous uniform distribution. If I'm going too fast, remember you can always go to the website and pull up these lecture notes later. Measures of central tendency. I hope these make sense. But the mean and the median are going to be the same number because this is a symmetric distribution. If I'm distributing the probability evenly in a uniform manner over all of the possible outcomes, then it's going to be symmetric. And the center of this distribution is going to be halfway between the lower bound and the upper bound. So A is the lower bound. B is the upper bound. And if I want the center of this interval, I take A plus B divided by 2. That gives me the midpoint. And since this is a symmetric distribution, the mean and the median are the same. For the mode, we say that the mode does not exist. Or you can write capital DNE. Stands for does not exist. Because if you really think about it, the distribution mode is supposed to be the outcome with the greatest probability. And yet, if we have a uniform distribution where all of the outcomes have exactly the same probability, no outcome has any more probability than any other, well then, there isn't a mode. Once again, look at the formula for the variance. The variance, we would need to know that formula for a test, so write that down on your little page of handwritten notes. This would be variance for the continuous uniform distribution. And then what do you do if you want the standard deviation? The standard deviation is always the square root of the variance. So those are our 3 new distributions today: normal, exponential, uniform. We can do some examples after this. But questions so far? Anybody? Okay, here's the question. Suppose you randomly select an MNU student and you measure the student's height. For these questions, assume the height of MNU students is normally distributed with mean of 66 and standard deviation of 3. What is the probability of selecting a student that's exactly 67.01234567 inches tall?
Didn't you say it was 0?
It is 0. Yeah. It's possible, right? I mean, it's entirely possible that somebody has this exact height, but the probability that the student we select has exactly this height, is 0. Because more than likely, the student is going to have a different height. I mean, right? Even if the student's height was really, really close to this exact number, the probability is still 0 that it's going to be exactly that number. I hope that makes sense. It just, you know, when you have a continuous random variable, there's no probabilities for exact outcomes. The probabilities only appear when you take a range of possible outcomes. Like, what's the probability of selecting a student that is shorter than 65 inches? When we have a normally distributed random variable, and we're asking a question like this, we need to first take the z-score. And the z-score is going to be my measurement minus the mean divided by the standard deviation. So my measurement is 65. The mean is 66. My standard deviation is 3. So my z-score is going to be negative 0.33. And so the probability I'm concerned about is the probability that a student's z-score is going to be less than or equal to negative 0.33. And this is a question for the standard normal distribution CDF table, because it's a less than or equal to probability. So when you've got a less than or equal to probability, we use the CDF table. So we pull this out and we say, my z-score is negative 0.33. Here's negative 0.3 on this row. For 0.33, I would also need to grab this column. And at the intersection of that row and that column, I see the probability 0.3707. And of course, the table gives this probability to us as a decimal, but if you want to convert it to a percent, you just multiply by 100%. And that's your answer. You can say the probability is 0.3707, or you can say the probability is 37.07%.
Can you just assume that it's equal to on this, even though it just says the student shorter than 65 inches? It doesn't say equal to.
Oh, yeah. So I understand what you're asking. It's a really good question. So I'm glad you asked. The probability that x is going to be less than or equal to 65 is going to be the probability that x is less than 65 plus the probability that x is equal to 65. Right? Because this symbol means less than or equal to.
But how do you know it's equal to if it just says the student is shorter than 65 inches? Like, does that still count? Is that what you're saying?
Great question. So what is the probability that x is exactly 65?
Couldn't do it, it'd be 0.
Yeah. Since this is a continuous random variable, the probability that x is exactly equal to 65 is 0. And if this term is 0, because the probability of getting an exact outcome for a continuous random variable is always 0, well, then that means the same thing. It doesn't really matter whether or not I use the less than sign or the less than or equal to sign when I'm talking about a continuous random variable. But I am really, really glad you asked this question because it's not the same for discrete random variables. So a week and a half ago, we were talking about discrete random variables. We were talking about the binomial distribution, the Poisson distribution, the discrete uniform distribution. And for discrete random variables, there is a probability that you get exactly a particular outcome. There is some probability that's not 0 that I could catch exactly 3 fish in one day. So for discrete random variables, less than or equal to is not the same thing as less than. And so you're asking a really, really good question. There's a video on YouTube I want to recommend to you guys if you have. Okay, so if that is still a burning question that you're really curious about, you can always look at that later. Next question.
I have a question.
You do?
How are we supposed to look at that and know which one to use?
How are you supposed to look at this question and know that we're supposed to use the CDF?
That part and also, well, the CDF, if it's shorter than, or if it's like less than or equal to?
Yes, less than or equal to is
always use
CDF.
CDF for
Mhm.
all the distributions?
Yep.
Okay. Now, how am I supposed to know to use the one you're talking about, the continuous versus the discrete, just based off that one question?
Okay.
Because I have no idea.
When a variable is normally distributed, I'm going to tell you that it's normally distributed. You'll see the words normally distributed appear in the question.
Okay.
Like I said, I'm going to use your homework questions when I write the test.
Okay.
So if you look at the homework I passed out at the beginning of the class, I use the words normally distributed when this happens. How do you know that this is a continuous random variable? The normal distribution is a continuous probability distribution. So if you see normally distributed, then you know this is a continuous random variable. Good questions.
Isn't there different kinds of continuous random variables?
Yeah, that's true.
Okay.
So earlier this lecture, we were talking about the exponential distribution. If a variable is exponentially distributed, that's also a continuous random variable.
Okay.
Yeah, let me summarize again for you what we were working with here.
Like, I know they're all continuous, but I just don't know how to pick which one between the continuous ones now.
So your 2.5 homework only asks you about discrete random variables. Your 2.6 homework only asks you about continuous random variables. On your test, I'm going to mix these questions up and give you both types of random variables, but you'll know whether or not the random variable is discrete or continuous based on what distribution it follows, right? Binomial, Poisson, discrete uniform are always discrete random variables. Normal, exponential, continuous uniform are always continuous random variables.
So the wording for the continuous is the normal distribution.
Or exponential. Or continuous uniform.
So it will say one of those in the question.
No, not necessarily. We also talked about this on the very, very, very first day of class. Like if you go back and watch lecture recording 1.1, we talked about the difference between a discrete random variable and a continuous random variable. Discrete random variables have to be a countable number of possible outcomes. Like a discrete random variable would be like, okay, how many students are in the classroom right now? There can only be a discrete number of students. There's either 30 or 31 or 32 or 33, but there will not ever be 31.5 students. But for a continuous random variable can take on any value within a range of possibilities. So a continuous random variable might be like, I don't know.
Someone's height.
Yeah, somebody's height. Somebody's weight. If we pluck one of Alexis's hairs and we measure it across a ruler, that would be a continuous random variable because the height of her or the length of her hair could be anything in a range of values. It doesn't necessarily have to be a whole number of inches. And so that's the main idea, is that like you should be able to read a question and determine if the random variable is discrete or continuous based on like what are the possible outcomes? Is there only a countable number of possible outcomes, or is the possibilities kind of a range of possibilities where it could be anything inside the whole range?
So the difference between them, so if you were to read a question, so you figure out it's discrete or continuous, you have three options.
Mm-hmm.
So then how do you go through those three options? Like,
that's a really good question. Can we save that for the end of lecture? I just want to make sure I get through the rest of the notes first, and then I want to answer that question. But it's just going to take me a little bit longer to answer that. All right, the probability of selecting a student taller than 63 inches. And we've got 26 minutes left in class, so I'm going to kind of speed up and go a little bit faster here. But the probability of getting a student taller than 63 inches, well, this is the complement of getting a student shorter than or equal to 63 inches. And so that's going to be 1 minus the probability of getting a student shorter than 63 inches. And the first step is always to calculate a z-score. If we are in the business of the normal distribution, we're going to calculate z-scores. So we'll do 63 minus 66 divided by 3. That's going to be -1 for my z-score. Then we have to look at the CDF, because the CDF function is telling us the probability of less than or equal to. So let's look up the CDF less than or equal to -1. And that's 0.1587. And 1 minus 0.1587 is 0.8413, which is 84.13%. What's the probability of selecting a student between 64 and 67 inches tall? So you've seen a question like this about a week and a half ago. And it goes like this. I'm going to take the probability of getting a student less than 67 inches tall, and then I'll subtract away from that the probability of getting a student less than 64 inches tall. And what I'm left with is just the probability of getting a student between 64 and 67. And so this is, again, a matter of finding the z-scores and using the CDF table. And so the z-score for 67 is going to be 67 minus 66 over 3. So that's 0.33. And then the z-score for 64 is going to be 64 minus 66 over 3, which is negative 2 over 3. And then this is where you use your CDF table twice to look up those probabilities. Since the CDF is the probability of less than or equal to, we look up these probabilities in the CDF table, and then we subtract them to get your answer. Again, I'm trying to move quickly because I'm already feeling the timer now on how much time we have left in class to cover all this material. So let's then ask, what is the height of the student who is taller than 95% of his or her peers? And that means I know the probability I want is 0.95. Now the question is, what's the threshold? What is the K value? Where the probability is going to be less than or equal to some number and make that probability equal to 0.95. This is a question for the quantile function. And so we're starting with a probability of 0.95. So let's go to my standard normal distribution quantile function. I'm looking for 0.95. Here it is. And that corresponding z-score is 1.6449. And then how do I convert a z-score into a measurement? Well, I have to multiply the z-score times the standard deviation. And then I have to add the mean to get my measurement. So my mean is 66. My z-score is 1.6449 times the standard deviation is 3. So 66 plus 0.6449 times 3. I get 70.93. So if you find a student that is 70.93 inches tall, they would be taller than 95% of their peers, according to this problem, right? And so the next question, what's the height of the student that's only taller than 15% of his or her peers? And the next question, you're going to do the same thing. This time the probability is 0.15. Then use that in the quantile function to look up a z-score. And then to get the measurement that you want out of your z-score, you do the mean plus the z-score times the standard deviation to get you a particular measurement. All right, what's the distribution mean? 66 inches. What's the distribution median? 66 inches. What's the distribution mode? 66 inches. Because the normal distribution is a symmetric distribution, all of the measures of central tendency will be the same for a symmetric distribution. What's the distribution variance? Well, the standard deviation was 3, so the variance must be 9, because the variance is always the standard deviation squared. All right.
Wait, so if it's an asymmetrical distribution, would the most
No. Hold that question, because we're about to do an asymmetrical distribution next. The exponential distribution is asymmetric, right? Like, this is, this is the case for the exponential distribution, the mode is always 0. But we also did some other distributions a week and a half ago. I keep referring back to the 2.5 lecture. When we were doing our lecture on section 2.5, we had some cases where, like for the binomial distribution, the mean, median, and mode aren't necessarily the same. Sometimes they're the same and sometimes they're not. When we were looking at the Poisson distribution, the mean, median, and mode were not necessarily the same. Sometimes they are, sometimes they're not. Really, these are not the only distributions, right? These are the only ones we're going to talk about in our intro to statistics class, but that's not the end of the whole story of statistics, right? There's other probabilities that people want to calculate and discuss, and there's other distributions out there. If I were to go to Wikipedia and look up probability distributions, common probability distributions and their applications. We could have a log normal distribution, a Pareto distribution. In the realm of discrete distributions, there's a hypergeometric distribution, and there's also a continuous beta binomial distribution, and there's a lot of different probability distributions that people study in statistics. Later this semester, we'll talk about the t distribution. But what's my point? Most of these distributions are asymmetric. For most of these distributions, the mean, median, and mode aren't the same. For the ones that we talk about in class, in terms of symmetries, this is symmetric, this is symmetric, this is symmetric. And these other ones are not necessarily symmetric. So, anyways, we're working on these problems. We're trying to do as much as we can in 15 minutes. Suppose you are the afternoon manager at Taco Bell and you typically expect to see 20 cars go through the drive-thru during the first hour of each shift. So this is what I would call an expected frequency. And if I see an expected frequency in my word problem, that gives me a clue that I'm either looking at a Poisson distribution problem or an exponential distribution problem, because both our Poisson distribution and our exponential distribution used expected frequency as a parameter. The way I can tell the difference is a Poisson distribution is counting a number of events. An exponential distribution is asking how much time passes in between the occurrence of these events. And this question is asking, what is the probability of seeing the first car drive up at exactly time t equals 5.314159? So that's an exponential question. We're not dealing with Poisson distribution, we're dealing with an exponential distribution, because we're talking about how much time in between cars arriving. And what is the answer to the first question? Yep. The probability of getting exactly this random outcome for a continuous random variable is 0. What's the probability of seeing at least one car drive up in the first 5 minutes? Well, that's going to be the probability that the time between these random events is less than or equal to 5. So this is a question for the CDF of the exponential distribution. And the CDF of the exponential distribution has the formula 1 minus e to the power negative lambda k. And for us, that k is the number 5, and my lambda is the number 20. So in my calculator, I'm going to type in 1 minus e to the power negative 100. See what I get? Wait a minute. I made a mistake. This is expected frequency in what units? Cars per hour. But this is not hours, this is minutes. So I need to do one of two things. I can either convert 5 minutes into hours by doing 5 divided by 60, and then I get the first fraction of an hour. I can do that. Or alternatively, I could convert 20 cars per hour into the equivalent, how many cars per minute? 1/3 cars per minute. That's okay too, because it's 20 cars per 60 minutes, so you simplify the fraction, 1/3 of a car per minute. So now let me try this again. Let me try this again, and we'll use lambda equals 1/3 cars per minute times 5 minutes. So I'm going to have 1 minus e raised to the power negative 5 divided by 3. Let's try that. And now I get 0.8111 as my probability. The probability of seeing at least one car drive up in the first 5 minutes is 81%. What's the probability of seeing no cars drive up in the first 4 minutes? Well, the probability of no cars in the first 4 minutes is saying that the probability of the time between cars being greater than 4, and that's the complement of the probability being less than or equal to 4. So this is the CDF applied again here, where let me distribute the minus, and I'll get 1 minus 1 plus e to the negative 4 divided by 3. 1 minus 1 is 0, so in my calculator I type in e raised to the power negative 4 divided by 3. Let me try that again. I got 0.2636. So there's a 26% chance we're not going to see any cars for the first 4 minutes. What's the probability of seeing the first car arrive between t equals 3 and t equals 6? This would be the probability of getting x less than or equal to 6 minus the probability of getting x less than or equal to 3. And to do both of those questions, I need the CDF. So in other words, I'm going to have negative e to the negative 2 power plus e to the negative 1 power. You got to, simplify, or maybe you don't simplify. Maybe you just put it in your calculator and it works. But negative e to the negative 2 close parentheses plus e to the negative 1. My calculator tells me that's 0.2325. 23%. What time corresponds to a 50% probability of seeing the first car drive through? So I want to know, what is this threshold that would give me a 50% probability? And that's a question for the quantile function, not the CDF. The quantile function, and that is something like this. Let me double check, because you can always write this down on your notes page and bring it into the test, right? But I just want to make sure I got the right thing. It should be negative natural log of 1 minus p divided by lambda. Negative natural log of 1 minus p divided by lambda. Cool. So for us, the probability we care about is 0.5. So 1 minus 0.5. And then I divide by lambda, which was 1/3. Dividing is the same thing as multiplying by the reciprocal. And so I could do this, minus natural log of 0.5 times 3. 2.079 minutes. So in other words, there's a probability of 50% that I'm going to see the first car drive through in the first 2.079 minutes. What is the distribution mean, median, mode? Again, these are formulas that you have written down somewhere. What was the median of the exponential distribution? Natural log of 2 divided by lambda. So natural log of 2 divided by 0.333333. It's like 2.079. The mode is, and sorry, that's the sign for the mean. The mode is 0 for an exponential distribution. The variance is the standard deviation squared, and the standard deviation for an exponential distribution is the same as the mean. So the variance is 9 this time. Okay, this last question, let's talk about this for 1 minute before we have to do something else. Alice spins a spinner and measures the angle the spinner makes with its starting position. So, a spinner means you've got this kind of circle with a little pin in the middle, and you are going to spin it somehow, right? And you're going to look and see, where is it pointing? What's the angle measure from where it started? That would be kind of a silly example of a continuous uniform distribution. For the continuous uniform distribution, because, if we get the spinner moving fast enough, then I would say any particular location on the spinner has equal probability of having the little thing land on it. And there's not a countable number of possible outcomes. It could land any range of angles between 0 and 360 degrees. And so this is a continuous uniform distribution with lower bound 0 and upper bound 360. The probability of getting an exact number of degrees would be 0, because it's a continuous random variable. And there's other probabilities that we can calculate using the cumulative distribution function. There's some angle measures we can calculate using the quantile function. We've got formulas for the mean, median, and mode, but here's the thing. I've got 4 minutes left. Nora asked a great question. She said, how can I practice identifying what distribution to use? Well, if the probabilities are equal among all of the possibilities, we know it's uniform. If the outcomes are countable, it's discrete. If the outcomes fall in a range of possibilities, it's continuous. Maybe the trickiest one is figuring out the difference between binomial and Poisson. For a Poisson distribution, you're going to be given an expected frequency. For a binomial distribution, you're going to see a certain number of trials with a probability of success in each trial. But here's what I want each of you guys to do before Friday. Go to chatgpt.com. Ask ChatGPT, please give me a list of 20 application problems where you describe either a binomial, Poisson, normal, exponential, discrete uniform, or continuous uniform distribution. Then let me try to identify which distribution is used. And if you've never used ChatGPT before, like, it's kind of good at this kind of things. Question number 1. A quality control inspector inspects 10 light bulbs and records how many are defective. Each bulb has a 5% chance of being defective. What distribution is there? Binomial. Because each light bulb is a Bernoulli trial. It's either defective or it's not defective. So that's a binomial situation. Number 2, the number of emails a customer service rep receives per hour follows a pattern with an average of 12 emails per hour. So how many emails are we going to get in the next hour? What distribution would that follow? If I ask you how many emails we're going to get in the next hour, that's a Poisson distribution because we're counting a discrete number of emails. But if I ask you how much time will pass before we receive the next email, that would be an exponential. If I ask you the time in between emails. Yep. But anyways, you see my point. This is how you can use ChatGPT to study. And you can tell it your answers. It'll tell you what you got right, what you got wrong. It's pretty good.